So we're now ready to do a big formula. And in particular, by the end of this session, we're going to be able to answer the question, how many patterns are there, side swap patterns, juggling patterns, with period n using exactly b balls? Or at least we'll give one reasonable answer. But before we get there, we need one more technique that's going to help us. So we're going to begin with bars and stars. Now, the goal of bars and stars is really about counting, and a lot of combinatorics boils down to, well, let's count different things. And oftentimes they phrase it in terms of, well, we have some balls and we want to put them into boxes. But then there's sort of the question, well, what can you say about the boxes? What can you say about the balls? In other words, are the boxes, are they more or less identical? It doesn't matter what box is which box? Or are they distinct? And same with the balls. So when we talk about bars and stars, we're talking about a very particular problem where we have a collection of objects. These are our balls, and they're going to correspond to the stars. We'll explain where the phrase bars and stars comes from. And they're identical. So we can't distinguish one from the other. We're going to put them into boxes or to groups. But each group is distinct. So it's like each box has its own label. Box number 1, box number 2, and so forth and so on. So we're going to look at the ways to distribute k identical objects into n distinct groups. All right, so how do we do it? Well, the answer is we're going to use two things. We're going to use dividers, which are going to act as the bars, and we're going to have the stars, which are our objects. And what we do is we think about, okay, suppose we want to have some number of groups, the number of boxes, if you will. Well, how many are there? So let's suppose you wanted to have 4 boxes. Okay, well, one way we can think about it is we can take it and divide it up into 4. So we're going to have 3 dividers. So then there's 1, 2, 3, 4. So now we have our 4 boxes. Now, what do we do with our objects? Well, the answer is we put them into the boxes. So we can put them in some number of ways, and we don't have to put anything in a particular box. So this would be the case if we had 1, 2, 3, 4, 5 objects, and we're putting them into 4 different groups. So how do we get different arrangements? Well, we just rearrange how things are positioned. And of course, there's all sorts of arrangements. So it turns out that the number of ways to do it is the number of ways to distribute these dividing lines and the objects. And so what do we see? Well, we see that there are k objects. All right, that's easy enough to see. And we're going to use n minus 1 dividing lines. So however many groups there are, one less dividing line, because we're going to go on either side. And so the objects, these are our stars, and the dividing lines, these are our bars. So it really boils down to saying, well, how many ways can you distribute these? Now, the answer is, well, we know how many total things we have. We say, oh, there's k plus n minus 1. See, that's the total number of things. And now we just have to say, well, where do we put the bars? Or, of course, we could say, where do we put the stars? So in other words, where should we choose the bars to go? And so this right here is saying, okay, let's choose the location of the bars. And of course, you could have, alternatively, if you wanted, chosen the location of the stars. But it's a very simple idea, very simple idea. So that's why we call it bars and stars. We're just saying, let's think about the ways we can represent a way to distribute the object. We use dividing lines and the objects themselves, and we look at all possible arrangements. And there you go. Very easy, right? Not so bad, not so bad. So let's try an example. All right. Alice, Bob, Carol, and Dan are at the farmer's market, and they're getting oranges. And in how many ways can they collectively buy 12 oranges? So that means that we know that among these 4 people, they bought a total of 12 oranges. And now notice there are 4 distinct people. They have names. These aren't just random people. So there's Alice and Bob and Carol and Dan. All right. So, well, look, an orange is an orange. There's 12 of them. So here, this is like, oh, we have these identical objects which we're distributing among the people. Now, it could be the case that one of them just buys 12 and the other 3 don't buy any. They might all buy 3 each. There's lots of different possibilities. But the key idea here is we have this collection of identical objects being distributed among distinct things, in this case, distinct people. Bars and stars, tailor-made. In fact, it's almost perfect, exactly what we need. All right, so what's the answer? All right, well, we know that the number of people is 4. These are our groups, places where we're going to be distributing our oranges into. And of course, we have our objects, which are our stars. These are our 12. Okay, so according to our bars and stars, well, what we do is we say, look, it's going to be, you add n, nk, and subtract 1. And remember, the subtract 1 is because when we have n groups, we have n minus 1 dividers. So we'll write it as 4 plus 12 subtract 1. And now, well, we can either pick where the dividers are, which is 4 minus 1, or we could pick where our stars are, our objects go. That would be 12. And they're the same because of symmetry. So, all right, 4 plus 12 minus 1 would be 15. 4 minus 1 would be 3. 15, choose 3. And whatever that turned out to be. All right, great. Well, wonderful. We have an answer. Now, there's a second part to this problem, which says, well, how does the answer change if we know that Carol has at least 4? So in other words, Carol is a big believer in vitamin C. So she said, look, I'm going to make sure I've got plenty of oranges, get my vitamin C intake going. All right, well, what happens? Now, what are we doing? Well, if we think back to what's happening, so we can think of our situation here, it might feel like, well, is it really still bars and stars? We still have our 3 dividers, but the problem is that we sort of have this condition here. So let's think about how we can approach this problem. So before we begin, we have this extra constraint, right? That says, look, we need to make sure that Carol has at least 4. Now you might say, well, we can go through and do lots of various counting, but the easiest thing is to say, let's just make sure that that constraint is satisfied. So maybe we can think of it as Carol went in at the very start of the farmer's market and grabbed 4 oranges. All right, great. So we'll throw some oranges into Carol's slot. So already, there we go. And of course, what's left? Well, the answer is we still have 8 oranges left. So there's a collection of 8 objects over here that haven't been placed. Now, what do we do with these? And the answer is we're going to take these 8 objects and we're going to distribute them among the 4 groups still. So now it's still the same bars and stars kind of counting, right? We're still looking at how many ways can we distribute some identical objects among a group of distinct people. But the only difference is now there's just fewer objects to distribute. So if you have extra conditions, one of the things that you can think about is there a way that we can sort of pre-satisfy those conditions? All right, let's just check off those boxes first, and then let's see what's left over to do. Now in this case, what's left over to do, more bars and stars, but it's hopefully a little bit easier, right? So what do we have? Well, we still have the 4 people left because we're told that Carol has at least 4. She could still go back and buy more. Nothing wrong with that. So, all right. And now the oranges that are left are our 8 oranges here. So we're going to distribute our 8 objects. So, number of ways to do that. Bars and stars, 4 plus 8 minus 1, right? The number of groups plus the number of objects, subtract 1. Then just remember what to choose. Either the number of groups minus 1 or the number of objects, right? It's either the number of bars or the numbers of stars. So let's see, 4 plus 8 minus 1 is 11. So we get, there's 11. Choose 3 ways for this to happen. That's it. There we go. It's not so bad. And in general, the bars and stars arguments and the problems that are related to them aren't so bad. You might have some extra conditions, and oftentimes it's just a matter of saying, how can I satisfy these conditions, and thinking about what you can do. All right, good. But now the important question. What do bars and stars have to do with counting juggling patterns? So let's go back to our boards. So here we have our nice basic board, and we're going to do it for n equals 5. But in general, you can think of for any arbitrary n equals 5 is just nice because we can actually put it all down. And what do we have? Well, we start with minimal patterns. All right, great. So that corresponds to rook placement. So we'll have our rook placement, and we'll place our rooks in some hopefully mildly interesting way. You know, that's always our goal, is to be mildly interesting, if not more than mildly interesting. All right, there we go. There's our rook placement, right? 1 rook in each row and 1 rook in each column. Great. Now, this has some very nice properties. This particular pattern is the pattern 2, 3, 4, 1, 4. And one of the things we saw is, hey, this is going to need 3 balls to juggle. How do we know? Well, because there's 3 balls underneath. Now, that's important. We'll come back and talk about that a little bit more. But remember, this is just a minimal pattern. We can now sort of create all the other patterns, in some sense, by starting with the appropriate minimal pattern, not just one, but there's some minimal pattern that we can start with, and then we can bump up. All right, so how do we think of bumping up? Well, what we can think of happening is that there's a collection of tokens available for us to use, and we have this big collection. So let's put our extra tokens here. Now, in theory, of course, there's just, unlimited tokens available for us if we wanted to. We could use as many tokens as we want. And what do these tokens represent? Well, we talked about if you have a minimal pattern, you can add n to any particular throw, and it's still a pattern. And of course, minimal pattern or not, you can always add any multiple events. So what we can think of doing is taking our tokens and saying, how do we change our throws by adding an n? So for each token we place, we add an n somewhere. So for instance, if I put a token here, now what's the pattern? Well, it'll be 2. This now becomes an 8 because it's a 3 plus you bump up once. So 2, 8, 4, 2, 4. But of course, I could bump up multiple times. I could bump this one up quite a lot, right? There's no limit to how many times I could bump up, and I can just distribute these tokens in any which way I want. And there we go. So what's this? Well, it's quite a more challenging thing to juggle. It'd be what? It'd be 2. Here, we started with 3, but we bumped it up 3 times. And each time we bump up, that means add 5. So it's now 18. So 2, 18, that'll be a 9, 7, and this will be a 9. It's still a pattern. And so what do we see? Well, how many balls do you need? Well, the answer for how many balls you need is however many come from the minimal juggling pattern, which corresponds to these blue tokens. That was our minimal pattern, plus 1 ball for every green one that we placed, right? Because every time you add n to a throw, you increase the number of balls in your pattern by exactly 1. So now we say, great, fantastic. So we have ways to make everything. And now we say, oh, hey, suppose we wanted to make a very specific number of balls? Well, okay, so let's reset here. Now, remember our initial pattern, we said, look, it has 3 balls already because there's 3 balls underneath. And suppose we said we want exactly 7. Okay, well, that means we have 4 balls to spare. And so we would say, all right, move these aside. They're not going to be used. So now we have 4 tokens to place. And we can place them anywhere we want. And lo and behold, that'll give us a pattern with exactly 7 balls. Now, you might say, well, what if you wanted not exactly 7? What if you said, look, I want less than 7? All right, well, that says we can place at most 3 tokens, right? And what can we do? Well, we can place all 3 tokens if we wanted to and get a pattern, great. But we don't even have to place all of them. We could just place 1 or 2 of them. Or we could say, look, we're just fine with the minimal pattern. And so now we say, aha, we have these different ways that we can count patterns with some prescribed number, or in particular, less than some prescribed number. So, all right, let's look at our answer. How many juggling patterns are there with period n and with less than b balls? Now, you might ask the question, why are you specifying less than b balls? That seems really kind of a weird constraint. And the answer is because the answer is nice if we specify it that way. And so that's the reason. I would totally agree with you when you say it doesn't seem like the most obvious thing to count initially. But, of course, oftentimes, you often see math, we do things in sort of unusual choices at the beginning. And the reason that if you ever see an unusual choice happening in math, it's because, oh, it turns out that this unusual choice helps you at some point. That's why we did it. Okay, so we're going to have less than b balls. All right, so what's the key? Step number 1 is you have to understand the sum. So there's the sum over k, and then there's the Euler number, nk, we're going to talk about that, and then there's this binomial coefficient. Now, after bars and stars, this will look a little bit familiar. Okay, so let's think about all of our pieces here. So, first off, what can we say about k? What is k? What does it represent? And that's important to understand because we're trying to understand all of our pieces. So k here, this is the number of balls in, oops, I don't know how to spell the word balls. I'm a juggler, I should be able to do that. So the number of balls in a minimal juggling pattern. Okay, so in other words, we're saying when we sum over k, we're summing over all of the patterns which have exactly k balls in their minimal juggling pattern. Now this nicely relates to this first term, the Eulerian number nk. That is how many minimal juggling patterns of period n with exactly k balls are there. So in some sense, what you could think of is you could have written the sum in a different way, which is sum over all the minimal patterns, and then for each one, talk about how there is to bump things up. So what we're doing is we're sort of collapsing it a bit and saying, look, we're just going to sum over all the k and say, well, how many are there for any particular k, where k is the number of minimal, k is the number of balls in that minimal pattern. All right, good. Now, so that explains this first term, the Eulerian number nk. How many juggling patterns are there of period n with k balls? Now to our second term. Okay, so the second term, it's a binomial coefficient. And what's happening here? Well, it does feel like bars and stars. So let's dig into what's going on. So let's jump back and take a look at our diagram one more time, just so we can sort of get an idea of where things are coming from. So what's going on here? N is the size of the board. All right. So you might think, all right, so that says we have N groups. Hold on, we'll get there. So we have K from the placement. So K corresponds to how many balls are underneath. How many balls are left? So in other words, how many balls are there down here that are going to be bumped up? Well, remember, we want less than B balls. We've already placed K. So that says that down here, if you look in this slot, we're going to have K, B minus 1 minus K. That's how many pieces we have available to bump up, right? Because less than B says at most B minus 1. And we've already gone K based off our board placement. So we have B minus 1 minus K left for us to place. So that tells us these are acting like our stars. Now, how many groups do we have? Well, we can place things in any one of these N positions, or we can leave it in here. So when we think about it in terms of the number of groups, we have a total of N groups here plus one more. So that means that we have N plus 1 groups. And to put that in another way, if we think about it in terms of the bars, that means we have exactly N bars. All right, so we've got N bars corresponding to our N plus 1 groups and B minus 1 minus K stars. And now we just think about how can we distribute things. And distribute things by either bumping up the throws or just choosing not to use all of our bumps and having some smaller number of balls. So by bars and stars, what do we see? Well, again, we have N bars, B minus 1 minus K stars, and we just choose where the bars go. So this is bars and stars. In other words, how can we bump up that pattern in all possible ways and make sure that the number of balls we have is B minus 1 or fewer? And that's it. That's it. Okay, and every pattern that we produce that way is distinct, and every pattern that we want to be counted shows up somewhere, which is perfect. We have an answer. It's not the most beautiful answer, but there's still space, so we're going to make it beautiful. All right, well, what are some things we can do? Well, we're going to work on rewriting as we go down. So to clean it up, in our next step, you might say, well, not much has happened with the second term, just a little bit of rearrangement. See, here, the minus 1 minus K moved around, so it became N minus K minus 1. Now, the big thing here was with the Eulerian number. You'll notice it started with NK and became N minus K minus 1. Well, why? Well, the answer is symmetry. So this is the symmetry of the Eulerian numbers that says, hey, you know, if you look, if you read it one direction on the row, it's the same as if you read it the other direction. All right, now at first glance, you're like, great, okay, so you rearrange some numbers and you use symmetry in a weird way, but why do that? Well, the thing is, you say, hey, look at these pieces now. Look how nice they are. They look the same because they're the same. And now we're going to take advantage of our notation. You see, we have this sum over all K. And what happens? Well, we just say, look, let K run over all values where things make sense. We aren't specifying. And this can come in handy. It says, you know, what we can do is do a little bit of name change, or if you like, a substitution. And here's our substitution. we're going to replace n minus k minus 1. We're going to call that L. We can change names. That's perfectly fine. And so, in our next step, what happens? Well, the Eulerian number becomes now NL. Our binomial coefficient, L plus B, choose N. Now, of course, as you sum over all K, it's the same as summing over all L, because it's just a change of names, but it's still a nice sum. So I'll say, great, all right. So we did some symmetry, we did a little bit of name changing, and what does that give us? Well, the sum that we have right now is a beautiful sum. In fact, it has its own name, and we've talked about this, and this is called Warpitsky's identity. And it turns out that this has a very nice, very clean answer. So when we sum over all these possibilities, this Eulerian number NL, binomial coefficient L plus Bn, it becomes B to the N. And that's it. That's cool. Like, wow! It's such a clean answer. Now, in some sense, if you're, I don't want to say if you're a real mathematician, but a mathematician would start going, whoa, that is a really beautiful answer. Look how clean it is. Look how beautiful it is. There's got to be a good explanation. And, well, we have one. And you might think, is there a better one? Yeah, there is, actually. We'll do that eventually, but not for now. But this is certainly one way to approach it. And so it's a really cool, really beautiful answer. But now you might say, hey, I like good answers, but I don't want to look at the number of juggling patterns of period n with less than b balls. I want the number of juggling patterns of period n with exactly b balls. How do I do that? Well, okay, good question. And but now that we have an answer, what can we say? Well, what we can think about is, all right, we know that if you have less than b balls, then our answer is going to be b to the power n. Well, what if I wanted to change this and say I want less than b plus 1 balls? All right, well, how does that change the answer? Well, that changes it by becoming b plus 1 to the power n. Wow, okay, nice, cool. Now, what's the key? Well, if we think about what's happening here, we can think about, all right, we have some juggling balls, and this is all the ones which have less than b plus 1 balls. All right, there's our big collection of juggling balls. And now we say, okay, if you have less than b balls, if you have less than b plus 1, you also contain everything that has less than b. So inside of here, there's a little piece. It's probably a big piece, but there's a piece which says, here you have something that has less than b balls. And it's inside the less than b plus 1. Now, what are we interested in? We said, look, we want exactly b. Where does that fall? And it falls in between. So this little difference has exactly b balls because it's not less than b, but it is less than b plus 1. And so we say, well, that's great. Then what we need to do is we just take all the patterns with less than b plus 1, subtract all the patterns with less than b, and that's the answer. And so we end up with b plus 1 to the n minus b to the n. And there's our answer. All right. Maybe not quite as beautiful, but still pretty nice. So are we done? Is there anything left to say? And well, there could be. There could be. So let's think about it. for a second here. Suppose we ask the question, let's do something really simple, a small number. And we say, I want to have, say, 3 balls with n equals 2. Okay, so what's the answer? Well, of course, you can plug it in, and you can say that would be b plus 1 is 3 plus 1, 4 to the power of 2. So it's 4 squared, and then it'd be 3 squared. Okay, so that would be 16 minus 9, which is 7. All right. Now, what are they? Well, in this case, it's not so hard to figure out. You can actually write them all down. I'll write them down. 6, 0. And in case you're wondering, well, what does 6, 0 look like? 6, 0 would be if you could juggle 3 balls in one hand. I can't do that. But that's what it looks like, 3 balls in one hand. Yeah, 6 means it's a pretty tall throw, so you've got time. But there's also 0, 6. And now you could say, well, 5, 1. And also the pattern 1, 5. Now 5, 1, that's the 3-ball shower. That's pretty straightforward. There's 4, 2. And also 2, 4. And 4, 2, that's you hold a ball in one hand, and with the other hand, you juggle 2. Okay? All right. And there's 3, 3. Now you notice I put and, because, hey, 6, 0, 0, 6, they're essentially the same, as is 5, 1 and 1, 5. Really, the difference is where do you start looking, where do you start counting? In other words, when do you start tracking the pattern? So it shouldn't matter, right? It's the same pattern, because if we think about time as extending, I really don't care where I start in trying to find my period of length n. And so you might say, okay, I should, in some sense, not count both of these. But this formula will count them both. So you might say, all right, well, I should find a way to get rid of that. The other thing you might say is, hey, this last one you wrote down, 3, 3, that's the 3-ball cascade, our normal 3-ball juggling pattern. But does it really have period 2? It feels more like period 1. So does it count? Should it count? Well, it depends, of course, what you want to count. But in some sense, you could say, look, if I want to count, it has to have period, n, but not smaller and exactly b balls. And I don't want to count things which are the same by somehow changing where I start. Well, in that case, it's a smaller number, right? It's really down to 3. And the question is, well, how do we get down to that count? That's where we're going to have a little bit more discussion. So isn't it great? There's always more to do, right? More to do. It'll be good. But for now, at least we have a nice answer. And it's always good to start there. All right, see you again.